And of course, let me start by saying thank you so much to the organizers, Cecilia, Fabienne, and Yves, for giving me the opportunity of being here today. Useless to say, it's a huge pleasure, and honor. Thank you so much. So as Peter said, I'm gonna talk about some automorphism groups of algebraic curves in positive characteristic, and more precisely, what I have for you today is more or less the following outline. So I will start by fixing some notation and terminology about algebraic curves, and in particular, the protagonist of my talk, namely automorphism groups. And this will allow me to talk about 3 open problems that I studied during my PhD and after that. The first open problem is a very, very general question, which is the following. Imagine you are given an algebraic curve, and D is a prime, not equal to the characteristic of the field, P, in which your curve is defined. How large can a D automorphism group of your curve be? Can you find bounds with respect to the genus of your curve? Can you prove that they are sharp? Because you can find extremal examples. So this is an open problem I studied. The second one is zooming in a very well-studied class of algebraic curves called ordinary curves. They are those having the largest possible P-rank or Hasse invariant equal to the genus. And the question is similar. Can you tell me how many automorphisms your ordinary curve can have and find a sharp bound for that? Lastly, it is well known in the literature that if you have a curve with many automorphisms, I will explain what many means later, then the P-rank is actually the smallest possible, so it is equal to 0. The open problem from 2000 I studied, open problem 3, is how many automorphisms does it take to make sure that your curve has P-rank 0? And yeah, what I would like to do is to describe my contributions to these problems here. So let me just get started with some notations. During this talk with K, I will always denote an algebraically closed field of positive characteristic P. With X, I will denote a projective, geometrically irreducible, non-singular algebraic curve defined over K. So we have a projective variety of dimension 1. It lives in some projective space, let's say of dimension R, at least equal to 2. And as you know, every algebraic curve has a purely algebraic twin, one can say, which is the algebraic function field of the curve, which I will denote with K of X. And every curve is equipped with some properties that are invariant under isomorphism, what we call birational invariance. And during my talk, I will mostly talk about 3 such invariants. The first one is the genus of the curve G. It is a non-negative integer. There is several methods to compute it, and it is the dimension of a vector space of differentials on your curve, if you want. That's why it is non-negative. The holomorphic differentials, as they are called. The P-rank gamma of the curve that I mentioned already before, also called Hasse-Witt invariant, which is also a non-negative integer that is at most equal to the genus. The reason is simply because it is the dimension of a subspace of that of dimension G, the space of holomorphic and logarithmic differentials, in fact. Lastly, the protagonist of my talk, out X, the automorphism group of the curve over the field K. And this, if we want to be very formal, would be the automorphism group of the function field of the curve. But more geometrically, we can think about it as a group of transformations of the projective space in which our curve is living, having a faithful action on the points of the curve. So you have to imagine you have this group. It is permuting the points. The automorphism group is permuting the points of your curve somehow, with some orbits, and non-trivially. A tool that I will use often during my talk is that whenever you fix a finite automorphism group of your curve, call it G, then you can construct another curve associated to G, which people often call the quotient curve of X with respect to G. The notation I will use is the one you can see in the first bullet point of my slide, which is X modulo G, to denote it. The formal definition of this quotient curve would be it is the curve whose function field is the fixed field of the group G. So you have to imagine you have these 2 function fields and a Galois extension between the 2, and G would be the Galois group of this extension. More intuitively speaking, the curve Y can be thought as the curve whose points are the orbits of the group G in its natural action on the points of the curve. So G is permuting points, it has some orbits. If you think about these orbits as points, you get the quotient curve. And as you can imagine, the curve x and this quotient curve x modulo g are strongly related to each other. And also the bidirectional invariants are, in fact, strongly related to each other. A thing one can see immediately, particularly from the geometric intuition, I would say, is that it is possible to induce automorphisms on a quotient curve. As a matter of fact, if you imagine to choose an automorphism from the normalizer of the group G, then normalizing G means acting on the orbits of G. So this means that every automorphism from the normalizer will permute the points of the quotient curve. So unless it is acting trivially, and that's why we take the modulo G in the 5th bullet point, then it means you are inducing an automorphism on the quotient curve. So the quotient group normalizer modulo G is in fact an automorphism group of the quotient curve. The relation between genera and p-ranks of the curve x and the quotient curve are even stronger because of the famous Riemann-Hurwitz formula and Dorisch-Avarevich formula. They are cross formulas, as you can see, involving the genera and the p-ranks of the two curves, respectively. Now, of course, when studying automorphisms, the very first question would be, how many automorphisms can your curve have? This question was studied already in 1938 by Schmidt, and later on by other authors. Iwasawa, Tamagawa, Roquette, Rosenlich, Garcia, among others, and they proved that whenever you have a curve of genus at least 2, so not elliptic, not the line, not genus 0, then the automorphism group of your curve is finite. And this is nice because it means that you can use finite group theory as a tool to study automorphism groups. If the genus is 1 or 0, you have elliptic curve or the line, then the automorphism group is in fact infinite. And I would say that studying automorphisms in positive characteristic is particularly intriguing because exceptional behaviors can occur that you can't find in characteristic 0. In characteristic 0, one has the classical Hurwitz bound from 1892, which says that whatever automorphism group you fix of your curve, its order is going to be at most 84 times g minus 1. So you have a linear bound with respect to the genus. And this bound is well known to be sharp, to be attained. There is many examples of Hurwitz curves, very famous, the Klein quartic, which has exactly, in fact, 84 times g minus 1 automorphisms. So in characteristic 0, we have a linear bound with respect to the genus, and we know it is sharp. This bound is not true in positive characteristic. Actually, it is known to be true whenever you have an automorphism group of order prime to p, the characteristic of the ground field, because Hurwitz proof can be adapted to this scenario. But if your automorphism group has order divisible by p, this bound can fail in principle. The most famous example I can think of a curve in which this bound fails in characteristic p is the Hermitian curve at the top of the slide. If you fix q, your favorite prime power, the Hermitian curve, which is the curve with the plane model you see on top on the slide, has PGU3Q as automorphism group, the projective general unitary group. And its order is larger than 16 times genus to the 4th, so a lot more than linear, right? The question, of course, is at this point, can you tell me if you know how many automorphisms your curve has? What is your curve after isomorphism? Can you characterize your curve using automorphisms? And this question was studied by Stirnov first in 1973, who in fact proved that if you have a curve of genus at least 2 that has at least 16 times genus to the 4th automorphisms, your curve is the Hermitian curve, the one on top of the slide. So this means that when studying automorphisms, we really don't care about two large automorphism groups. If we have at least genus to the 4th automorphisms, we know we are the Hermitian curve. So the literature at that point became, okay, can you tell me then what happens if I have cubic many automorphisms or quadratic many automorphisms, so on and so forth. And in fact, the first person to study the cubic case was Henn in his PhD thesis only 3 years after Stirnov's result. And he could prove a very beautiful result, which is that if you have a curve with more than genus cube automorphisms, then your curve is going to be one of the 4 you can see in this slide, so with explicit quotients. The Hermitian curve is there, that we could have guessed, because it has genus to the 4th, right? So more than cubic automorphisms, but there is other curves. Suzuki curve, Roquette curve, just to cite 2 famous examples. It is worth mentioning that, in fact, all these curves that you can see in this slide have p rank 0. And this convinced the researchers in this topic that, in fact, having many automorphisms leads to having very, very small P rank. In fact, P rank equal to 0. This, more or less, was a connection, if you want, between automorphism group and genus. So the question is now, what about really the connection between automorphism group and P rank? It was, in fact, Nakajima in 1987 who studied this problem, proving all kinds of very beautiful results about this connection. In this slide, I collected 3 that I think are very interesting. The first one is the opposite of this P rank 0 case, namely, it proved that if you have an ordinary curve, largest possible P rank, then its automorphism group cannot be large, of order at most quadratic with respect to the genus. And second of all, bullet point 2, it could prove really that the P rank of a curve has an impact on the size of P groups of automorphisms, where P is, again, the characteristic of your field. In fact, as you can see in the middle of the slide, the size of a P group of automorphisms is upper bounded by something linear in the P rank, at least if the P rank is larger than or equal than 2. Not only, but it would also prove that if you have too many P elements in your group, if the cardinality of your P group is too large, then the P rank is equal to 0 again. And I like this result because somehow it's telling you that everything comes together nicely. As I said before, in order to have more than linear automorphisms, I need to have order divisible by P. And now we are saying the P rank has an impact on the size of a P group, and in fact, if you have a too large P group, you have P rank 0. So again, as you can see, these results come together quite nicely. When I was a PhD student, I had essentially some questions related to Nakajima's results here. The first one being, okay, we see the link between P rank and P groups of automorphisms, but what about D groups, where D is any other prime? Can you find something like Nakajima's results in this case? Second of all, in Nakajima's paper, one cannot find any extremal example for the bullet point 1. Namely, there is no curves that attain that bound with equality. So can you improve, maybe, Nakajima's bound to make it sharp? This is the second problem. The third one is that we saw from Hans' results that if we have at least cubic many automorphisms, we have P rank 0. But would square many automorphisms be enough? So can you find, this was the formulation of the open problem for 2000, can you find an optimal function f of g of the genus such that if you have at least f of g many automorphisms, then your curve necessarily has P rank equal to 0? And the claim the community had is that quadratic many would be enough, in fact. Cubic for sure will work, linear for sure will not, because there is many curves with linear many automorphisms and P rank not equal to 0. So the claim is quadratic maybe would be already enough. As I mentioned, I would like to describe what I did around these 3 open problems here. And before I go to open problem 1, let me just mention that, in fact, the reason why people looked at ranges of cardinalities of automorphism groups with respect to the genus is simply because if you do that, then you can combine the Hurwitz genus formula I showed you before to obtain strong restrictions on how your automorphism group can act on the points of your curve. A direct application of the Hurwitz genus formula already says, for example, that if your group, call it G, of automorphisms has at least 4 short orbits, as they are called. An orbit is short when you have a stabilizer that is non-trivial. So it is not as long as the cardinality of the group, right? A bit shorter. If you have at least 4 short orbits, the cardinality of your group is small. It's at most 4G. This means that if you want more than linear automorphisms, you're going to have at most 3 short orbits. But in fact, by looking at the proof by Hurwitz of its bound, 84 times g minus 1, one sees immediately that if you have a group of order that violates the Hurwitz bound, so larger than 84 times g minus 1, in fact, your group will have at most 3 short orbits, but in 4 only possible configurations. And at least one of such orbits is going to have a stabilizer of order divisible by p, what people call non-tamed short orbits. And I found that very, very intriguing, because if the idea in open problem 3 is to understand how quadratic many automorphisms with respect to the genus behave, one could imagine of going through these 4 cases one by one and trying to find the bound, assuming the action is exactly the one described. And I realized that if quadratic bounds for the first 2 cases are already available, which means that if you have an automorphism group with more than quadratic many elements inside, then the last two cases only can occur. And I realized that hence result, when we have those 4 curves, cubic many automorphisms, in reality, all fall into category 4. This convinced me that probably in case 3, also one could find a quadratic bound, which is what my contribution to open problem 3 will be. But this was just to give you an idea on how to combine, essentially, a bound with respect to the genus and the action of the group. I will go back to this later when talking about open problem 3. But let's go to open problem 1. So imagine you have a curve X, genus G at least equal to 2, D is a prime, not P. How large can a D group G be of automorphisms? This was one of the main topics I studied for my PhD thesis. And the reason why we decided with my former PhD supervisors, Gabor Kocsmáros, to study this problem is, first of all, that we knew we couldn't improve the case D is P. We have Nakajima's bound in that case, and Nakajima's bound is known to be sharp, because several authors, Stishnov, Giulietta, and Kocsmáros, among others, constructed so-called Nakajima extremal curves. So there is extremal examples. We can't improve Nakajima's bound. So what if D is different from P? In reality, a bound is known in characteristic 0 for this case. And it was proven by Zomorodian in 1985. He proved that in characteristic 0, if G is your D group, D is a prime, then its order is at most 9 times G minus 1. He also said that, of course, this bound can be attained only if, and this is intuitive, D is 3. Because to have equality, a power of D equal to 9 times G minus 1, then D needs to be a power of 3, because it's divisible by 9, right? And also G minus 1 needs to be a power of 3 as well. So G minus 1 is something like 3 to the k for some k. So what our idea was with my PhD thesis was to try to prove the Zomorodian results in characteristic P and prove that actually it is sharp by finding a machinery to construct extremal examples. What we obtained working on this together with Gabor Kocsmáros in 2020 is an improvement, not only a proof of Zomorodian results, but actually we could prove a sharper bound in the case in which D is larger than 3. The bound that we prove if D is 3 is Zomorodian result, 9 times G minus 1, but if D is larger than 3, then the bound reads 2D over D minus 3 times G minus 1. We could also prove that if you have an extremal example, so order 9 times G minus 1 for D is 3, then your group is non-abelian, which is interesting because it means the structure is more complicated of your group if you want. In my opinion, the most interesting case that one can study is definitely the case D is 3. Not only because the bound is larger in this case, but also because finding extremal examples for our bound for D larger than 3 is actually very simple, and already abelian groups attain it. If you consider, for example, fixing your prime D larger than 3, so at least 5, if you consider the Fermat curve of degree D, the one in the middle of the slide, then this curve has genus D minus 1 times D minus 2 over 2, because it is non-singular. And if you plug in the value of the genus in our formula, you will get exactly D squared. And an automorphism group of order D squared can be found very, very quickly, because we can just map x and y to lambda x mu y, where lambda and mu are this root of unity. Of course, in this way, you are preserving the quotient of the curve, so you have an automorphism, and the order is D squared. So what I'm trying to say is that if D is not 3, then we have a bound, and we have extremal examples for every D. So in this case, we know our bound is sharp. So our question was at this point, okay, what can we say if D is equal to 3? Imagine we have an extremal example for D is 3, order 9 times G minus 1. How does G look like? Can you use the structure of G to build up a machinery to construct extremal examples? Since in the extremal example for D is 3, the group is not abelian, we decided to zoom in this case. So let's assume our group G is non-abelian. What can we say? Remember that a group that is a D group, where D is a prime, has a non-trivial center, right? Every D group has a non-trivial center. So we can find in the center a subgroup, call it D, of order D, the smallest possible. Take the quotient curve with respect to your Z, of order D in the center, the curve x bar. Then what we prove is that if the curve x bar has genus at most 1, so very small, then my group can't be extremal with respect to our bound. unless d is equal to 3 and it is extremal with respect to our bound. What is this theorem saying? Well, in principle, it is not obvious that you can apply it, right? Eventually, you take the quotient with respect to z, and you get a curve that is of genus at least 2. But if this happens, the group z we took the quotient from is contained in the center. So my entire group G normalizes it. This implies that my quotient curve has the entire G modulo Z as automorphism group, which is large. We are just removing a D from the order, right? In fact, what we obtain is that if this theorem doesn't apply, then the quotient curve is again extremal with respect to our bound. But nicer, no? Because we are decreasing the genus. We are making the group G smaller. So this means that whenever this theorem doesn't apply, you can construct another extremal example, but with smaller genus and with a smaller group. And you can imagine to go on this way, up to when the genus of your curve becomes smaller and smaller and smaller. And sooner or later, when you take the quotient modulo Z, you will obtain something of very small genus, at most 1. So this theorem will apply. So up to use this machinery of reduction, we decided to zoom in what we called the minimal extremal examples for d is equal to 3. Namely, the extremal example, order 9 times g minus 1, where this elliptic quotient, genus 1, can be found. So where this theorem applies. So the question is, how does G look like in this minimal or elliptic, say, case example? And can you find an extremal curve explicitly? What we did was, zooming in this elliptic case, to realize, using properties of elliptic curves, that the center, actually, of my group G cannot be too large. It has order at most 9, not only, but maximal subgroups of our group here, G, are all the ones of index 3 only. Those are definitely maximal, index 3, but only those. And exactly one of them is either abelian or minimal non-abelian. This result sounds a bit artificial, but the thing is that there is a lot of literature about 3 groups. And in particular, 3 groups that satisfy this last bullet point were listed and classified in terms of generators and relations. First by Blackburn in the abelian case, we are in 1958, and more recently in 2012 for the minimal non-abelian case. So what I'm trying to say is that thanks to this proposition, we could describe the group G explicitly in terms of generators. And we have only 4 cases that are possible. So far, what this means is that we have a bound, 9 times g minus 1, and if we have an extremal example of elliptic type or minimal type, we know how the group looks like. So it becomes even more important to say, okay, can you find an extremal example, or are just describing a group that doesn't exist, essentially? And I would like to show you the intuition of our machinery to construct extremal 3-Zomorodian curve for every possible genus. So this is what we want to do, essentially, right? We want to construct a curve that is of genus G. G minus 1 needs to be a power of 3, as we said before. So the genus is going to be something like 3 to the h plus 1. And we want to have a group G of order 3 to the h plus 2, because it is 9 times G minus 1, right? This is what we want to achieve. Not only, but we want to find something of order 3 in the center, such that when we take the quotient curve, this is elliptic. This is what the previous theorem was saying. When we take the quotient with respect to something in the center, the quotient group will have order 3 to the h plus 1 only, and it's going to be an automorphism group of the elliptic curve. This is what we know so far. If you want to construct this curve, maybe you can look at the picture from the opposite side. You could imagine to fix an elliptic curve, to fix a group of order 3 to the h plus 1 there, and then find a clever extension of degree 3 of your elliptic curve that allows you to lift your group from the elliptic curve to your extension in exactly 3 ways. Because in this way, you get a group of the right order, at least, 3 to the h plus 2. If you choose this extension in the right way, maybe you can even force it to have the right genus, so 3 to the h plus 1. This was the idea that we had. So what did we do? We started with an elliptic curve that we knew pretty well, which is the one written in the slide. We denoted with J the corresponding translation group, which is abelian and it is infinite. People also call it Jacobian group. We fixed the point P minus 1, 0, 1, which is an inflection point of this elliptic curve, and the automorphism alpha bar that you see in the slide, essentially just mapping y to epsilon times y, where epsilon is a cubic root of unity. And of course, note that alpha bar is fixed in the point P because it has 0 y coordinate, the point P. So alpha bar is fixed in P, is fixing a lot more, fixes also other 2 points, in fact, which means that it can't be in the Jacobian group because the Jacobian group is transitive. So it doesn't fix any point on your elliptic curve. At this point, we wanted to fix a group, G bar on the elliptic curve of order 3 to the h plus 1. So the question was, how can my group G bar look like? What we prove is that our group G bar, unless it is contained in the Jacobian, which we don't want, will always be something like h bar, semi-direct product, the group generated by alpha bar, where h bar is nothing else but a maximal subgroup of index 3 given by the intersection with the Jacobian. So the intersection with the Jacobian is a maximal subgroup, abelian of index 3, and we have a complement given by the alpha bar that I defined before. Our group can also be generated by 2 elements only, which is quite convenient. Okay, but with this theorem, imagine we start with our elliptic curve from before, we fix G bar of order 3 to the h plus 1, the group we want to lift. Now, since my group can be generated by 2 elements, as a minimal generating set, this means that the quotient of G bar with the Frattini subgroup, as it is called, has order 9. The Frattini subgroup is a subgroup that is the intersection of all maximal subgroups, but if you remember, it tells you when you take the quotient that the quotient has order 3 to the minimal number of generators. So in this case, 3 to the 2 would be. That's why it has order 9. So my Frattini subgroup has order 3 to the h minus 1, I'm dividing by 9, and being the intersection of all maximal subgroups by definition, it is contained in h bar, because h bar has index 3, so it is a maximal subgroup. This information was important for us, because it means that my Frattini subgroup here is contained in the Jacobian. So it doesn't have any fixed points, it just acts with long orbits everywhere. And this allowed us to create a picture, which is the one I try to propose you here, which is the following. Take the point P I defined before, the inflection point from before, and denote with θ1 the orbit of the Frattini subgroup contained in P. You know how long this orbit is, because the Frattini subgroup being in the Jacobian has only long orbits everywhere. Then call with θ the orbit of h bar contained in P. That also you know how long it is, because also h bar is contained in the Jacobian. But since h bar normalizes the Frattini subgroup, then the orbit θ contained in P is the union of 3 orbits of the Frattini subgroup, because it needs to act on the orbit of the Frattini subgroup. So we have a picture of this type, and I invite you to observe that in fact my θ here is not only an orbit of h bar, but in fact it is an orbit of G bar, the big group I fixed at the beginning. And the reason is because what is not in h bar is obtained by alpha bar. And alpha bar fixes P and normalizes h bar. So when you normalize, you act on the orbits. But if you fix P, then you need to act on that orbit containing P. So in fact, θ is an orbit of G bar. The reason for all of this construction, I try to give you the intuition of, is that now we could use a result by Korczmarov-Nogień-Pace that allows you to say that if you take a line R joining P and the point Q of your choice from the second orbit θ2, then the third intersection point with the elliptic curve, we expect 3, right, is going to be a point from the third orbit. So you have this nice division between the 3 points in the 3 orbits in your line. This line can be written explicitly, of course, as well as you can write explicitly the quotient of the inflectional tangent at P, which is just a line intersecting at P with multiplicity 3, in this case. At this point, remember, we want to find this clever extension of degree 3, right? In fact, what we can do is that we can consider as a function in the function field of our elliptic curve the ratio of the 2 lines, R over the inflectional tangent. The reason is because we know the divisor of this line very quickly, because the numerator vanishes at P, Q, and R with multiplicity 1. The denominator vanishes only at P with multiplicity 3, as we said. So Q and R are going to be zeros of our function, the numerator vanish, and the denominator, well, we have 1 minus 3 as valuation, so we get a minus 2p. The function that gives rise to the degree 3 extension I mentioned at the beginning is in fact going to be the product of T and all the images of T with respect to elements of the Frattini subgroup, what people would call the norm, if you want, of T. This function can be arbitrarily ugly as such, but you can predict the divisor of it again. Because when you multiply functions, the divisor is just the sum of the divisors. But what happens when you apply f to the divisor of T? Remember that P, Q, and R are contained in 3 orbits of the Frattini subgroup. And f is in the Frattini subgroup. So what f is going to do is just going to move P to another point of the orbit theta 1, Q to another point of the orbit theta 2, R to another point of the orbit theta 3. And you are doing that for all possible f's. So what you are doing is that you are moving around P, Q, and R in the orbits theta 1, 2, and 3 in all possible ways. All in all, what I'm trying to say is that the divisor of W is just going to be minus 2, one orbit, plus another orbit, plus another orbit, theta 2 and theta 3. This was crucial because we knew that G bar was acting on the orbit theta, so it is shuffling around theta 1, theta 2, and theta 3 in some ways. So either it is fixing them or it is permuting them. And this was important because it means that G bar of W over W is either a constant. This happens exactly when you are fixing the divisor of W, so you need to map W into a multiple of W. Or when you shuffle the 3 orbits around cyclically, then a direct computation shows that your divisor, G bar of W over W, is in fact a multiple of 3. This made us believe that maybe this ratio, G bar of W over W, is a cube in the function field, and this happens. So this means that we can predict that for whatever element of G bar we have, then G bar is going to map W into a cube times W. This was the ingredient to lift the group G bar, because now I can show you how the extremal example looks like. As you can see, I have 2 equations. One is the elliptic curve I started with. The second one is the extension of degree 3, z cube equal to W. First thing we could do is to prove that it has the right genus, 3 to the h plus 1. Now we want to prove that G bar can be lifted in 3 ways as an automorphism group of X. Why is that true? Well, because if I fix arbitrarily an element from G bar, then to define an automorphism of X, I need to tell you where I map X, Y, and Z. Well, you're just going to map X and Y wherever G bar was mapping them at the beginning, and then Z to V times Z, where V is the cube that I found in the previous slide. The reason for that is that, of course, a G defined in this way is going to fix the first equation because it does what G bar does, and G bar was an automorphism of that curve. What about the second equation, though? If you apply G to the left-hand side of the second equation, you will compute G of Z cube. Just replace what G of Z is here, is V times Z. So you get V cube times Z cube. V cube by construction is G bar of W over W. This, we chose it in this way. What about Z cube? But Z cube is just W from the quotient. So as you can see, you can force with this trick a cancellation of W, implying that G of Z cube is just G bar of W. What is G bar of W? But W is a function of X and Y. And G is doing whatever G bar was doing in X and Y. So G bar of W is G of W. So as you can see, I could prove that G of Z cube is equal to G of W. So I'm preserving the second equation as well. And this proves that I can lift the automorphisms of G bar in exactly 3 ways, the choice that I have for V. At this point, we were curious to see if all the 4 cases for the group G I showed you in the previous slide with generators actually occur. So we use magma. It's kind of algorithmic, right? To construct extremal examples, and all 4 cases I mentioned before, in fact, arise. And one can give also very ugly-looking explicit equations. This was everything I have for the first open problem. What about the second one? As I mentioned, Nakajima studied automorphism groups of ordinary curve, so genus equal to the P rank, obtaining a quadratic bound, 84 times G squared minus G, without extremal examples. In my PhD thesis, together with Gabor Kocsmaros, I've been trying to understand if I could improve this bound here, and we could. In fact, we could prove, for example, that if you have an ordinary curve in odd characteristic and a solvable automorphism group, then its order is a lot lower than quadratic. It is roughly genus to the 3/2. And as far as I know, this is the best bound that is known for ordinary curves. And while I was a PhD, and after my PhD, I also tried to understand if this bound was sharp, of course, because it is what was missing in Nakajima's paper. And working with Giovanni Zini and Pietro Speziali, we managed to construct families of extremal examples, what we call generalized Artin-Mumford curves. So we have finally a sharp bound here. I will not propose the proof for you because it's very, very long, but at least let me give you an idea on why we have this hypothesis solvable group. Solvability of your group implies, by the property of solvable groups, that you have a minimal normal subgroup that is elementary abelian. This is a well-known property. If you call it S, then you can take the quotient with respect to your S, so you have a nice normal subgroup. You can look at the quotient group. It is going to inherit a lot of automorphisms, as we did before, right? And this means that if you assume that the bound G/3/2 is not true, then also your quotient curve is going to violate that bound. So you can create the same machinery I did before by taking all these quotients one after the other, or continuing obtaining extremal examples, but with decreasing genus. At a certain point, like we did before, we are going to hit the case in which taking this quotient, you are going to get a curve of genus at most 1. When this happened, in this case, I could prove that the genus is necessarily 0. And when the genus is 0, it means you have the line as a quotient curve. And automorphism groups of the line are very, very well known. So I could use properties of those to obtain a contradiction. This is more or less the strategy. So the solvability allows you to find a nice normal subgroup to which apply this machinery. This is what I'm trying to say. But of course, you have to imagine that I was not very happy with it as a PhD student, because of course I didn't like p-odd as an assumption. I wanted also p's too. And also I didn't like the group needs to be solvable. So of course I tried to generalize these two results. And together with Pietro Speziali in 2019, we managed to prove the result also in characteristic 2 for solvable groups using different old literature about solvable groups in characteristic 2. Bound is still the same, genus to the 3/2, which is nice. But for non-solvable automorphism groups, we obtained a bound that is better than Nakajima's one, genus to the 7/4, but we don't have an extremal example. So this means that maybe this bound can be improved. But as far as I know, there is not an optimal bound for non-solvable automorphism groups of ordinary curves. So it is still an open problem in that case.
Your first theorems are all characteristic 2, really?
Oh! Thank you, yeah. Sorry. Okay. Apart from that, let me just finish my talk by talking about open problem 3. Namely, how many automorphisms does it take to have P rank 0? And as I mentioned before, when you have more than linear many automorphisms, then only 4 possibilities for your 3 short orbits or less can arise. And if some quadratic bounds were known for the first 2 cases, all hence curves, more than cubic many, fall into case 4. So my idea in 2023 was, what if I can obtain a quadratic bound for case 3? So when I have exactly 1 untamed short orbit. This result would be interesting, I believe, because it tells you that if you have at least quadratic many automorphisms, then case 4 occurs. So you know how your group is going to act. So this can, allow you to maybe obtain the proof of open problem 3 and prove that your curve also necessarily has P rank 0. In 2023, I studied this problem, and particularly case 3, where you have exactly 1 short orbit, and I could in fact obtain a quadratic bound, which is the one that you can see at the beginning of the slide in red. So I could also prove, in fact, in the same theorem that if you have at least quadratic many automorphisms, the P rank of your curve is 0 modulo P. And in fact, I could also prove that it is 0 the P rank. But I have 2 assumptions I couldn't get rid of. Either the genus of your curve is even, or you know something about the stabilizer of 2 points. If one of these two conditions is true, then I could complete the open problem. So we know the quadratic many automorphisms will work to have P rank 0, but again, this is still open in principle. All I could obtain is that if you have more than quadratic automorphisms, then your group is acting in a very, very specific way. I would like now really to finish my talk by giving you an idea on how you could prove the quadratic bound for case 3, so when you have one short orbit, and the proof is in fact very intuitive. What I did was, okay, let's assume by contradiction my bound is not true, so I have that my group has one short orbit, satisfies case 3, and I have more than quadratic many automorphisms. Call with O your orbit, and take a point from there. Call it P. I would say you have two cases. Either your orbit is very trivial, so it contains only P, or it contains something else. Imagine first it contains only P. This means that your group has an orbit of length 1, P, so it fixes P, and it doesn't fix anything else. It's the only short orbit, right? Lucky enough, the stabilizer of a point for an algebraic curve is very, very structured. It has, as a normal subgroup, its 0P subgroup that I called GP1, and the complement of that is a cyclic group of order prime to P. So what did I do? I took the quotient with respect to GP1, because in this way I knew that H would be an automorphism of the quotient curve. And I did same trick as before. How does this quotient curve look like? Can it have genus larger than 2, larger than or equal than 2? In this case, I could prove that my group has order at most 5g squared. So I got immediately a contradiction, because I was assuming it was larger than that, right? What if it is rational? Again, if it is rational, then I have line as a quotient curve, and everything is known there. In particular, I know that cyclic groups will fix 2 points. But I can't allow that, because my group was fixing 1, nothing more than that. So I obtained immediately a contradiction in this way. The interesting case, I would say, and it is where the ugly constant 336 comes from, is where you have more than P in your orbit. In this case, using Dorian-Shafarevich formula, I could prove that either I have P rank 0, which is all in all what I want, right, in the open problem, or if I don't have P rank 0, then GP, the stabilizer of the point P, has exactly 2 short orbits. One is P, and the other one I don't know. I call it O2. Since I wanted to prove P rank equal to 0, I said, okay, let me try to exclude that the positive P rank can occur first. In this case, I have these 2 orbits, P and O2, but my big group G has only 1 orbit. So there is no possibility, but O needs to be the union of P and O2. And that is nice, because if you think about it, P and O2 are orbits of the stabilizer of P. So this means that the stabilizer of P acts on O minus P transitively. This is what you would call a 2-transitive group. And when you have a 2-transitive group, then you have all kinds of literature listing 2-transitive groups. So what I did was to explore that literature, take all 2-transitive groups one by one, and try to obtain a contradiction. And this is where 336, the constant from before, comes from, one of those explicit 2-transitive groups. Then I said, okay, I know that if I have more than quadratic many automorphisms, I have P rank 0, but can this actually occur? And then I realized that P rank 0 actually can't occur from Dorian-Shafarevich formula. So what I'm trying to say is that I got always a contradiction. So it means that I was starting with something not true, namely the possibility of having a group of order larger than 336g squared. This is how I proved essentially this result. Let me now really finish my talk by saying that, in fact, having at least quadratic many automorphisms and satisfying the last remaining case, case 4, can happen. There is many known curves with quadratic many automorphisms in this scenario. G-curve, GK curve by Juliette and Korczmaros, 2009. It has quadratic many automorphisms. It satisfies case 4. The Scablon curves over Suzuki and recurves, they also have quadratic many automorphisms. They satisfy case 4, as we proved in 2017. So this makes me believe that finding a classification like N for all curves of having at least quadratic many automorphisms is going to be difficult, because there is, in fact, many nice examples of curves satisfying that scenario. In my talk, I've been trying to give you an idea on how to obtain results about theoretical study of automorphism groups, but in fact, automorphism groups can be used in different applications also. And I tried to study, for example, applications in coding theory, together with my co-authors, Daniele Bartoli, Luciano Cuos, and Giovanni Zini. For example, automorphism groups can be used to construct locally recoverable codes from function fields, or to construct self-orthogonal AG codes, which are used for quantum codes, but also to obtain more, theoretical applications. One can imagine to use automorphism groups to classify algebraic curves. And together with Daniele Bartoli and Fernando Torres, we did that for maximal curves. So those with the largest number of points over a finite field, right? And also, and this is something we are investigating recently together with Peter Bellen, our students, and also Luciano Cuos and Giovanni Zini, the possibility of using automorphism groups to construct new maximal curves, and also to distinguish between known maximal curves to, make sure that the new construction we are providing is really new, in a sense, not isomorphic to what is known. This is also some kind of applications we are studying right now at DTU. And I mean, at this point, you may wonder what's next. What can one do? And if I had to describe some dreams I have regarding what I would like to do in the future, for sure, I would like to go back to studying unsolvable automorphisms of ordinary curves with the purpose of obtaining a sharp bound also there and close that chapter. I think that would be very, very interesting. Also constructing ordinary curves with many automorphisms. And of course, I would really like to understand if the open problem regarding how many automorphisms it takes to have P rank 0 can be closed completely, saying, okay, quadratic many will work. And this, as I mentioned, will require to being able to remove some extra assumptions that I had from the results from 2023. Equally interesting would be, in my opinion, to understand, does the automorphism group have an interaction with other invariants of your curve under isomorphism? We saw in this presentation, at least I tried, something involving the genus, something involving the P rank, but what about something like the A number? That is also an invariant of the curve. Is there any connection with automorphism group? I don't know. Maybe yes, maybe no. But I think it would be interesting to understand that. And what can we say about maximal curves in general? Can we just describe all automorphisms of maximal curves somehow? So these are all questions I think are nice and would make sense to analyze to some extent. But this is really everything I have for you today. So thank you so much for your attention.
Okay, thank you for your talk. So you asked us some questions, but maybe people here want to ask you some questions as well. Let me explain that if you want to ask a question, you will have to use this microphone because everything is recorded like that. So, any questions? Yes, I'll come to you with the microphone.
Yes, great talk. I had
Thank
two
you.
related questions. One is you gave bounds for different, two extreme values of the P rank, 0 and G.
Yeah.
Is there a proposed bound that incorporates both the P rank and the genus that would interpolate between those results?
I don't think so. At least not that I'm aware of.
And then my other question that would maybe give you data that would allow you to think about that was, is there an analog of the manypoints.org website for, say, manyautomorphisms.org that would give me extremal examples by, genus and P rank
I would love
in
to.
different characteristics?
I don't think there is. I think it would be super interesting, in fact.
Yeah, I think there should be.
Thanks.
Any other questions? Yes?
Yeah, I have a question. Like you mentioned all these bounds, and I mean, of course, the characteristic P makes the bounds not the standard ones.
Mm-hmm.
But do you know something, like in general, if you have a curve in characteristic 0 and you do the reduction modulo P, how the automorphism group can increase? And the other way around, if you have your curve modulo P,
Mm-hmm.
can you lift this curve into characteristic 0? And which part of the automorphism group can you lift with it? Do you know about?
I mean, I'm aware of papers that do that, like, for example, to considering characteristic P reductions of curves in characteristic 0 in the way that they knew that some automorphism groups would survive and hence study those. But I don't know if there is a systematic way, let's say, to study this problem. I'm not aware of that, at least.
Thank you.
Okay, so thank you for the talk. I had a question. So you try to classify the type of automorphism of the curve. So it's like finding the inertia of the curve when seen as a point on the moduli stack of curves, right?
Yeah.
And then a natural question would be trying to classify the residual germ of this stack. Are you aware of any classification on this? Do you plan to work on this? Or?
No, I didn't myself, but no, I'm not aware of that, in fact. No. Thank you.
Okay, any other questions? So if not, I have maybe one question. So there is always this thought that curves with many rational points have many automorphisms because there's much to act on, maybe there are long orbits, whatnot. But are you aware of any, let's say, lower bound on the automorphism group of a maximal curve or something like that?
No. I mean, there is, for obvious reason with this quotienting kind of construction, there is a lot of maximal curves with many automorphisms available. But it's also possible to take, for example, the Fermat curve that doesn't have a lot of automorphisms, roughly linear with respect to the genus, right? So that is already suggesting that, in fact, one can go pretty down, right, with the order. And I wouldn't be surprised if one could construct even maximal curves without automorphisms as such. No, I don't think there is a priori lower bound possible in this scenario.
Okay, so last minute questions? No? So then we have a coffee break and we will resume at 11 o'clock.
Thank you.